Hello everyone, my name is MD Mursalatul Islam Pallab from Department of Computer Science and Engineering at Dhaka International University, and I am presenting this work on behalf of all 6 co-authors, MD Ashraful Mullah, Rashiduzzaman Rakib, myself, MD Mehdi Hassan and Adil Mahmoud Rion, and our corresponding author is MD Abdul Basit. Our paper is titled FairCF, Fair Counterfactual Explanation for Student Academic Performance Prediction. Agenda. Here is what we will cover: the motivation behind FairCF, our 3 contributions, the dataset, a quick correlation analysis, our methodology, the prediction benchmark, explainability results, how we generate counterfactuals, a fairness audit, and finally, the discussion. Limitations and conclusions also added. Introduction. Let's start with the problem. If we predict a student will score 61 out of 100, that number alone tells them nothing about which behavioral to change or by how much. That's a real gap. Counterfactual explains it by answering a much more useful question. What is the minimum changes to my inputs that would change the output? That gives directly actionable, personalized guidance. But there is a missing pitch in most of this work. Group fairness is rarely enforced. Recourse, meaning the ability to actually change your outputs, can be much easier for some student group than others. FairCF is our attempt to close that gap. Contribution. We make 3 contributions. First, an accurate regression model XGBoost achieved an R-squared of 0.725 on a large dataset of 6,607 students with 19 predictor features. Second, actionable counterfactuals. We use dice to generate them with a 96% success rate, and critically, we restrict changes to features students can realistically control. Third, a fairness audit using demographic parity gap analysis across gender, family income, and school type, which reveal a meaningful gap of 0.1 for income. Dataset. We used the student performance factor datasets, 6,607 students, 19 predictor features, and an exam score target ranging from 55 to 101, averaging 67.2. The features span behavioral variables like hours studies and attendances, ordinal variables like parental involvement and family, binary variable like genders, school type, and peer influence as a nominal variable. We used an 80/20 stratified split with a fixed random seed for reproducibility. Correlation analysis. Before modeling, we looked at what actually correlates with exam score. Attendance and our studies lead every other predictor with correlation of 0.58 and 0.44. And importantly, both are actionable. Variable features. Gender and school type, on the other hand, shows near zero correlation with performance. That's an early signal that motivates the fairness audit we present later. Methodology. Here is the FairCF pipeline, summarized and analyzed as algorithm work. We train an XGBoost regressor on the training data, compute shape value to identify the most influential predictors, flag low-performing students below a threshold of 69, generates 3 diverse dice, counterfactuals as flagged student, restricted to actionable features only, and finally compute a demographic parity graph for each sensitive attribute. The pipeline returns both the counterfactuals and a fairness report. Prediction performance. We benchmarked 3 regressors, random forest, gradient boosting, and XGBoost on a held-out test set of 1,322 students. XGBoost win on every matrix, lowest RMSE, lowest MAE, and highest R-squared of 0.725. That makes it the backbone of the entire FairCF pipeline. Explainability. SHAP. Using SHAP, we found that actionable predictors dominate the model's decisions. Attendance with a SHAP value of 1.99 and our studies at 1.40 are the top 2 drivers, and both are behaviorals, meaning students can actually change them. Socio-demographic factors like gender and school type scores below 0.03, which lines up nicely with the small fairness gaps we observed for those small variable letters. Counterfactuals generation. Here is how we generate the counterfactuals themselves. We solve an optimization that finds the smallest change to a student's input that pose their predicted score above the threshold, while keeping immutable features fixed. These immutable features are gender, school type, family income, and learning disabilities. Status thing a student simply cannot change. The actionable features we are allowed to modify are limited to 6: hours studies, attendance, sleep hours, previous score, tutoring seasons, and physical activity. Counterfactuals actionability profile. We tested this on 50 low-performing students and achieved a 96% success rate. 48 out of 50 got a valid counterfactual. Hours studies and attendance are changed most frequently across the 144 generated counterfactuals. But here is an interesting fact. Attendance demands the largest absolute adjustment, and an average of plus 24.4% points, while tutoring sessions only need an average change of plus 4.4 per month. In other words, tutoring is lower effort, more efficient lever for the same result. Illustrative example. Let's make this concrete with one student. Before 66% attendance, 0 tutoring session a month, predicted score of 69.4. The counterfactual recommendation rise attendance to 90%, that's plus 24 points, and add 4 tutoring season a month. The new predicted score is 70.8, crossing the passing threshold of 69. This is specific, bounded, and directly actionable, unlike a typical gradient-based Salesi map that just tells you which pixels or feature mattered. Fairness audit, measuring demographic parity. Now to fairness. We measure the demographic parity gap, the difference between the highest and lowest rate at which any subgroup is predicted to be a higher performer. A gap of 0 means perfect parity. We audited this across gender, family income, and school type. We closed demographic parity specifically because our goal was to test whenever the model produced systematically different favorable prediction rate across groups. We are upfront that other fairness metrics might be more approachable in other deployment contexts. This is an initial assessment, not a complete picture. Fairness audit, where parity shows up. Gender and school type both show near perfect parity. DPG values of 0.005 and 0.002. But family income tells a different story, a DPG of 0.1. High-income students are predicted as high performer 36.2% of the time, compared to only 26.2 for low-income students, a 10% point gap. That's a real signal of structural socioeconomic bias embedded in the training data. Discussion. A few key takeaways from all this. First, actionability isn't same as achievability. A 24-point attendance increase in ambitious, even if it's technically observable, while tutoring sessions are much more lower effort lever institutions can directly support. Second, on the income gap, we believe it likely reflects real socioeconomic disparity, like unequal access to tutoring or connectivity, rather than poor algorithmic bias. That means the right fix is upstream resource allocation, not just tweaking the model. And third, SAP and counterfactuals play a complementary role. SAP tells institutions where to invest, for example, in attendance support, while counterfactuals tells individual students and coaches exactly what that specific student needs. Limitations. We want to upfront about 3 limitations. First, we evaluated a single dataset with some synthetic characteristics, so multi-institutional and longitudinal validation is still needed. Second, DICE's a random search method can't guarantee mathematically optimal counterfactuals. Gradient-based or integer programming approaches might do better. And third, demographic parity is just one fairness notion among several. Equalized odds or individual fairness may be more approachable depending on the deployment context. Conclusion. To summarize, XGBoost with an R-squared of 0.725 and RMSE of 1.971 powers a unified pipeline that combines prediction, counterfactual explanation, and fairness audit for 6,607 students. 96% of a lower performing students received valid actionable counterfactuals, mostly around attendance and tutoring changes. And we found a meaningful fairness gap for family income, even as gender and school type showed near perfect parity. For future work, we are planning prospective classroom studies, multi-institutional data sets, and integration into digital mentoring dashboard. These are our key references. Thank you very much for your attention. I'm happy to take any questions.